right, we're going to take a look at section today 1.1, which is mathematics and problem solving. We're not going to get too far into it, as you can see, we only have about 12 minutes left. We are going to get started just a little bit. So the first thing I want to talk about is the 4-step problem solving process. So much of this is all written for you, you don't have to write any of these things down. But there's 4 steps, and of course, you kind of see that there's actually 5 written down, because I broke one apart. But I wanted to call it 4-step problem solving process, because that's what your book calls it. Okay? So I realize that there's 4 and 5, and that's not very good, but we're going to do it. So the first thing is to understand the problem. So this 5 steps is within step number 1 right here. So to understand the problem, we have to do a few things. The first thing you want to do is to think about, can the problem be stated differently? Is there another way to reword it or to restructure it? You may be familiar with doing some of that with children, right? If the problem says something about the word difference, and you can ask them, what does difference mean? Right? What does that ask them to do that mean? What is to be found or what is needed? What are we looking for? And there may be different ways when you describe that you have to figure that out. We'll talk about some different problems on strategies in a little bit. What are the unknowns? What do you not know? Okay, what do you not know about the problem? What information are you given in the problem? Good to know, because obviously they gave it to you most of the time you need it, right? Oh, so most of the time you need it. And then what information, if any, is either missing, or, if it was given, is not needed. Okay? Those are some details that we have to ask ourselves when we're trying to understand the problem. The second step that we have to do here is to devise a plan. How are we going to solve the problem? And this following list is a list. It's not exhaustive. Okay, it means there's more things you can put on this list. But this is some ways of thinking about and solving the problem or planning to solve the problem. So one way to do it is to look for a pattern. Right? You guys have seen that before, right? So one of the ways kids learn multiplication facts is by noticing the pattern of addition. Examining related problems to see if the same techniques can be applied. So if you did this problem and you used blocks to do this problem and you understood it, maybe you use blocks to do the next problem because you can understand that one as well. So applying the same technique you've used before. The third way is to examine a simpler or a special case. Some things make the problem a little bit easier to work with and think, okay, I did that easier problem this way, maybe I can sort of extend that idea of the problem to really supposed to be working on. D, make a table or a list. Are any of you list makers? I am. I'm a to-do list maker. In fact, I'll add things to the to-do list that weren't on them and mark them off if I've done them. Anybody else do that? Some nods, yeah. I'm a list maker. I really like this method. This is a method that just beckons to me. I make a lot of lists when I solve problems. It's something that I do a lot of. You don't have to, but you could. The fifth one, we're on 5th. Identify a sub-goal. Sometimes within problems you have to solve one piece of it before you can solve what you were really asked to find. You guys see problems like that before? Right? So that missing piece of information, to find that missing piece of information to actually find what the real problem is you're asked to find. That happens sometimes. Make a diagram. Do we have any artists in here? Okay, doodlers? Yeah? Okay. Sometimes diagrams are really helpful. Give you a picture. Sometimes diagrams are especially helpful for young kids because they can get a grasp of the physical idea you're talking about better than they can an abstract idea of what you're talking about. So diagrams are often really helpful, diagrams, pictures. Guess and check. Do you like guess and check? Sometimes it's really helpful, and sometimes it is a really good way of doing a problem. Now, random guess and check is not what we're talking about here. We're not talking about randomly checking a number and something that's going to work and then randomly pulling something else. But sort of an educated guess and check, where we guess something and we check it and we say, okay, that ended up with an answer that was far too small. I need to adjust my original guess to make it more correct, to make it more appropriate. So guess and check is one way. Working backwards. Now, I know you guys work backwards before. Do you know in the context you work backwards? You work backwards when you said, I don't know how to do problem 32, but 31's in the back of the book. So I'm going to flip to the back of the book and I'm going to look at 31's answer and I'm going to see if I can figure out from that answer how they did the problem. Right? This is what we do. And it's good reasoning. Working backwards. Another place you may have worked backwards before is doing mazes. My daughter likes to work mazes backwards. They're a lot easier backwards than they are forward. So you've used this sort of strategy in other areas before, so working backwards is a legitimate plan. The last one is to write an equation. And you might be surprised that the writing an equation kind of approach is occurring far younger than very few that have seen it used before. So my understanding, and I can't remember, my understanding is that as early as grade 4, students are writing equations. So equation writing is a legitimate way of doing problems. And the cool thing is that you may choose to do a problem with a table or list, and someone else may choose the problem to do the problem using an equation, and you can both be right. And that's good. And that's good reasoning, that's good thinking. We don't want to stifle sort of what your natural inclination is or how you would intuitively approach the problem. All right, so then you actually have to do the plan that you devised. So we're going to carry out the plan. So when we carry out the plan, step 3, you're going to implement the strategy or strategies that you figured out. Maybe it's more than one. And you're going to actually do them. Figure out what the answer is that you obtained from that. To attend to precision in language and mathematics use, so you're precise, because mathematics is precise. So we want to be precise in what we're doing. And you want to check the steps along the way, either formally, like you actually take a number and plug it back in, checking your work, right? Or intuitively saying, is that reasonable, right? If I find out that I'm supposed to have 4.5 legs on that termite, is that reasonable? Yeah, okay, that's the kind of intuitive that it's talking about. And then keeping an accurate record of all work. Okay, so this is step 3, and you'll notice there isn't a step 4. So I was wrong when I said 5 and 4, it's 4 to 3. So it was a 4-step process, and I only showed you 3 steps. The 4th step is checking your work. So it's not actually part of the problem solving itself, but it's part of finding out if your solution worked. So step 4 is not listed here, it's not written down. Step 4 of the problem solving strategies is actually checking to make sure your answer works. Again, both intuitively, does the answer make sense? And formally, does it check out with what information I was given that I was looking to find? Okay? All right, we're going to do one, I think, problem-solving strategy today. And this problem is Gauss's problem. So let me read the problem for you. This is actually like something that really happened in real life to this gentleman. His name is Gauss. And Gauss was a mathematician, and he was a rather intelligent child from early on, apparently. So let's see what he did. So when Gauss was in early grade school, his teacher gave the class an assignment, intending them to take a good deal of time. She asked the class what the sum of the numbers 1 to 100 was. Gauss answered almost immediately, and he did it using patterns. Okay, so can you imagine this teacher? Put yourself in that place, with those kindergartners in that class, or first graders or whatever, and you're trying to get them to do something. It will take them a little bit of time because you need to get something else done. That never happens, right? Of course not. Well, it did to Gauss's teacher, and so she gave them this problem that should have taken a while, right? Because if you count, or if you add up the numbers 1 plus 2 plus 3 plus 4, this would take you a while, especially if you were younger, right? And no calculators. This is well before calculators, okay? So let me show you what Gauss did. And what I want to show you then is how he did it using patterns. So the first thing is we're going to write down that we've got this sum, and we're going to call the sum S. And this is the sum that the teacher's asking them to find. And very legitimately, what she wants them to do is to do 1 plus 2, 3, 4, and so on, until we get to, say, 96, 97, 98, 99. Whoops, I ran out of space. Almost 100. That's a 0. Okay, so we're going to add these numbers in. Okay, so we could do that. I mean, we could add the numbers in order, and we could take as long as the teacher wanted us to, but that would take a while. So here's what Gauss did. Gauss noticed something. He noticed that if you take the number 1 and 100 and you add them together, what do you get? 101. And if you take the number 2 and 99, and then you add them together, what do you get? 101. And if you take the number 3 and 98, and you add them together, what do you get? That's kind of cool, isn't it? So we're going to do a bunch of times that we're going to add the number 101 together. Basically half the number of times that we have our sum. So we're going to have 101. Okay. So what we're going to do next is we're going to replace all of our numbers one at a time with the number 101. bunch of 101s. But what I really did is I replaced every single number with 101. That's more than I was asked to find, right? Because the 101 came from carrying two numbers up, and that added up to 101. So how much more than I need do I have? Twice as much, right? So instead of replacing a pair of numbers with 101, I replaced every single number with 101. In other words, the 1 at the beginning from 101 and the 100 at the beginning from 101. I replaced it twice. So this is actually twice as much as I needed, or 2s. I can still solve for s by dividing the 2 to the other side, agreed? Okay. There's one more thing I need to know. I need to know how many numbers I have. So how many numbers are there from 1 to 100? There's 100 numbers. And that's pretty nice, but what if it had said I started at 3 and I went from 3 to 100? What would I do? Well, I'd go back to the 1 to 100, which was 100 numbers, and I removed the number 1, and I removed the number 2. So how many numbers did I remove? 2 numbers from the 100 numbers, which would mean I had 98 numbers, okay? What if I had only the evens? I'd have half of them, right? I'd have 50 numbers. What if we're only the odds? 50 numbers, okay? So we want to count up how many numbers we have. In this case, there are 100 numbers here. All right, so I have 100 numbers. 101 is the numbers that I have. So again, do you really want to add 101 plus 101 plus 101? No, probably not. What could you do instead? We'll get to the 50 in a minute, but what can I multiply by first? Just ignore the left side. 100. So I have 100 numbers. All of those numbers are 101. Repeated addition, and we'll learn more about this detailedly. Repeated addition is just another way of describing multiplication. So I can add and thing together a bunch of times, and we want a shorthand or a shortcut way of doing it, so we multiply. That's what this is. I have 100 numbers. So this is the number of numbers. And this is the values I am adding. And that's equal to 2s. Remind me your name? Lydia? Okay. And this is what Lydia was talking about when she said times 50, because this 2 can be divided to the other side, right? Division. And if you want to divide first, this is 100 divided by 2, you could get 50. Right? So if you did 50 times 101, that's what she was getting her numbers. You could also just divide by 2 afterwards. In other words, you could multiply the 100 and the 101 together and get 1 0, 1, and then 2 zeros, and then divide by 2. And it doesn't matter what order you do the multiplication and division, you'll get the same thing. So either way you do it, what do you get when you divide this? There's a 5. It's not 500 though. 5,050, right? 10 divided by 2 is 5. This 10 divided by 2 is 5, but the 1 didn't divide at all. That's why there's a 0. So 10 divided by 2 is the 5 here, and then the 0 is down here. The other way you could have done it is you could have said this is 50 times 101 and multiplied that out either way. So Gauss found out that this sum is actually 5050, or 5,050. And that's his problem-solving strategy using patterns. Okay? Who says he's smart? Pretty good. I believe, if I remember right, I believe this was 6. Pretty smart. All right, we will pick up with this more again next time.